Okay, there's no real solution to the equation 10 to the x equals log base 10 of x. This is similar to a different question, the one that's you certainly might have seen before. And there's two in the problem sets. One is one we're shifted left, right. The other one is just shifted up, down, all right? It goes on to say that if you shifted A units vertically, the two graphs will eventually meet, initially at 1 point, but then at 2 points. Ideally, I would like to know when these two graphs meet at a unique point. Use Newton's method to find this point. So what I want to do is try to visualize what they just said. And what they're giving me over here is they're giving me an equation, log base 10 of x, and they're saying that there's no real solution to the problem. So what I'll do is just visualize it out. And I know what this looks like. This looks like this. This is y equals 10 to the x. And I know what this looks like. And what does it look like? It looks like this over here. They're actually inverses of one another, all right? Now, they're clearly not meeting, all right, in a real space. But what they say is you could translate this thing by either moving the log up, again, this is the log problem, or the exponential down, right? So what I'm going to do is I'm going to move the exponential down. So what I want to do is I want to move this thing down until these things just touch one another. All right, the way I would do that, I'll write this one down over here. It's going to be 10 to the x. And I want to move it down a units with the understanding that a is some positive number. All right? And I want to find out where they intersect. All right? And the way I'm going to do that is just, set them equal to one another. So 10 to the x minus a equals log base 10 to the x. The thing is, it's two unknowns there, and I really can't figure that out looking at it. Although I do know that I have to move it down. I could play around with this over here using a graphic software and get sort of like an approximation to it. I'm going to say, if you did that, you'd get roughly the number 2, all right? But what I want to do here is I want to say that if they do touch each other, they're going to be tangent to one another. So what I want to do is I want to take the derivatives of both sides. So I need a derivative of this thing over here. Again, if you can remember this, fine. Let's do the natural log of both sides. And that's going to be x natural log of 10. And that's going to be 1 over y dy dx equals ln 10. All right? So dy dx would equal y, which is 10 to the x, times ln 10. So I can do the left side. What do I get? I get 10 to the x times the natural log of 10. Now, the derivative of a is going to be 0, so don't have to worry about that. Now, let's do the log now. All right, this one's done. I want to differentiate the other side. And the derivative should be equal when they're tangent at some value for x. Well, I'm going to rewrite this guy, 10 to the y equals x, and then differentiate both sides. Well, I just differentiated the other guys. I guess really very similar, right? So what do you get? You get 10 to the y times ln 10 dy dx equals 1. Now I want to put a little problem over here. Certainly I do this, I get a y over here, and I don't want that. So what I'm going to do is a little differently, get my eraser out, and it's going to happen to you something that's not going to be very useful. And let me just erase this over here. And I'm going to erase this over here. And I'm going to just do it a little differently this time. I'm going to take the natural log of both sides. And what do you get? Y ln 10 equals ln x. Well, I can differentiate this. What do you get? Ln 10 dy dx equals 1 over x. And what do you get there? Dy dx equals 1 over x ln 10. And write that down. It's going to be 1, and then you get x ln 10. All right? So I have two equations, two unknowns. And what I like about the second equation does not have an a in it. So I can actually solve this. However, it looks like a really difficult equation to solve. So what I'm going to do is I'm going to try to use Newton's method. The first thing I'm going to do is just rewrite it. And I'm going to write it as, let's see, x times 10 to the x times the natural log of 10, that whole thing squared. what I do, I multiply both sides by x ln 10, and it's going to equal 1. I'm going to solve that for 0. You get x 10 to the x ln 10 squared minus 1 equals 0. Now, if you're going to use Newton's method in this one over here, what you have to do is define a function, and a function is about finding roots. What's a root where it equals 0? And this is a pretty easy problem to do using Newton's method. Okay, I'm going to post a video of me using Sage and coding Newton's method. I'm going to get an answer over there. And the answer that you're going to eventually get over here is going to be the x value. Right? You'll get an x over here, an approximate value for x. I'm just going to say the x is approximately 2 point something. All right, now what does that mean? You're going to shift this curve down 2 point some odd units down. All right, all right. I'm sorry, I made a mistake there. That's the x is 2.2. All right, the x is 2.2. I want to get the a. How do you get the a? You get the a by plugging it in here. Let me just go through that. All right, so the a, I'll write this over here for you. So 10 to the x minus a equals log base 10 x. That's what I just wrote over there. This is where the x is, but I need to solve for a, so it's going to be 10 to the x minus log base 10 to the x would equal a. All right? Take this number here. It's going to be a really long, complicated number. And plug it in here, and you're going to get the a. And the a is going to be approximately equal to, I want to see if I did that. You know what? I'm making another mistake, by the way. The x wasn't that number, but that was the, I'm actually reading over my Sage code. I made a mistake in copying. All right, let me erase this over here. This number here approximately is 0.14. By the way, it's a really long number. I'm not writing it down. And the a over here is approximately 2.23. All right? Now again, I look at this, and this does get shifted down the a units. And what's the a units going to be? This over here. Again, when I use Sage over here, which I'll post later with a video, by the way, it's a detailed number, by the way. Not only that, what we did, I graphed it out. And what I graphed out, I graphed out the log function. Looks like this over here. And that's going to be y equals log base 10 of x. And also graphed out the other function, and that looks like this over here. And again, when I put it down, I'm not saying I'm doing a great job, but I'll post this video, or actually I'll post a picture for you. And this can be some point of intersection, by the way. What's the x going to be? The x is going to be 0.137. And then someone says, I wonder what the other value is. The other value is going to be when the function, either the log function, is evaluated at that number. All right? And that's it. Again, there's a video posted of that. Thank you.